So, continuing the discussion on fuel injection systems, we will see in this lecture some of the physics which is involved, some of the forces which are involved in nozzles, fuel injector nozzles, and how do we control the fuel injection spray characteristics. We will also see some of the testing methods of these nozzles. So, let us see what are the type of forces. You will recall that in the very first lecture in the introduction, we have actually done one experiment in which I had some water in my mouth and I sprayed it and I showed it to you that depending on the pressure difference between the mouth cavity and outside, the spray characteristics can be varied. So, once you understand the process, then what are the underlying forces? So, let us see what are the underlying forces when we create a spray. So, when a spray is typically an example of an interfacial flow. So, what is interfacial flow? That means there are two phases. That is, there is an interface which is created. So, there are some examples. For example, when a droplet forms, when you put a droplet in water, let us say you will get satellite droplets like that, and this is a very good example of interfacial flow. There is a interface here, there is a liquid interface and an air interface, and this interface gets let us say destabilized, and various patterns can form, various surfaces can be created by applying the necessary forces. You have also seen a very simple experiment which you can do in your own bathroom, that if you put a very small let us say jet or a liquid oozing out from a tap, from a water tap, you will see that as it goes down, the area of cross section reduces and naturally, because it is getting accelerated by gravity. So, as the acceleration happens, the velocity increases, and for the same mass flow rate, as the velocity increases, the area of cross section goes down. The flow is accelerating. Now, something interesting happens as after a certain while, you can see waves appearing on the surface, you can see these waves, and after a while you can see that the amplitude of the wave has increased, and you can then later see that an individual droplet has also formed, a new surface has been created. In a similar manner, you can also see some droplets which are falling down. For example, tear drops can fall down, and as they fall down, they can make rivulets. Depending on the wetting characteristics of the. So, here basically there is a three-phase flow. That means there is not only air and liquid, but there is also a solid on which let us say the liquid is flowing. You can also have examples wherein you have seen, let us say, a liquid plug and a gas bubble going inside a typical capillary tube. For example, when you drink Coca-Cola, for example, you will have interfacial flow like that. So, there is liquid phase, there is gas phase, and there are distinct menisci or interfaces which are formed, and they, of course, there is a relative motion between the gas velocity and the liquid velocity. So, when we are dealing with such interfacial flows can also come on lab on chip devices. For example, here you see a particular droplet coming in, there is an obstacle because of which the droplet breaks down and then again reforms into one particular droplet. Now, depending on the velocity, the droplet may deform the interface may deform in different ways, and you can also get some small let us say droplets which are left behind. So, after the journey is complete, the droplet the volume has decreased because part of the liquid was deposited. So, now which phenomena dominates, what type of interfaces will be created, what type of instabilities will come in these interfaces, and what are the relevant forces which lead to such interesting flow patterns. Of course, as for IC engine operation, we are interested to make a jet, break down the jet as we have seen in the last class, and break it down into very small droplets of diesel. Now, as you will recall that when you do such a thing, we need forces. That means, if more, let us say, as soon as a new surface area is created, we need to do some work, and this work goes as surface energy, or it is stored as excess surface energy of this particular new surface which has been created. For example, when we are scooping butter, for example, from a block of butter, we have to do work, and naturally if it is a completely reversible process, then whatever energy you expend, that has to go into the surface energy of the new area which has been created. So, under these circumstances, if you see the scaling of forces, we have several forces. One is the viscous force. Now, the viscous force comes because it is a fluid, and as soon as fluid gets in motion, you have gradients of velocities which are created, and these gradients of velocities, as you all know, will lead to shear stress. So, there are viscous stresses. Naturally, the length scales are very small and you will have surface tension. This particular interface, there will be interfacial excess energy, and this excess energy is manifested as surface tension, which you all know. So, there is surface tension will also be there. Now, under certain circumstances, for example, in a capillary flow, for example, if this capillary was vertical in nature, then the gas phase will have a lower density than the adjoining liquid phase, and therefore, you will also have a buoyancy force. So, there can also be buoyant forces. Okay. So, these buoyant forces may not be directly applicable in an IC engine situation, but of course, the bond number, which is I will discuss that shortly, is an important parameter for creating the spray. At least the basic diameter at which the spray will come out will be a surface tension dominant type of a flow. So, there will be buoyancy, and then there will be and what is the last thing? The another force which is present in such systems is the inertia force. For example, the velocity will lead to the mass into velocity will lead to let us say momentum transfer, and this momentum transfer will lead to inertia forces because the material would like to remain at rest, but you are trying to accelerate it or giving it a velocity. So, there will be a inertia force which will be present in these systems. Now, depending on the situation, we may like to see the scaling of these forces. Okay. So, which force is dominant? For example, the viscous forces can be compared to surface tension forces, the buoyancy forces can be compared to surface tension forces, and the inertia forces can be compared to the surface tension forces. So, with these three forces you can make combinations and we can get three non-dimensional numbers. And what are these non-dimensional numbers? The viscous to surface tension ratio is called as the capillary number. The buoyancy force to surface tension forces are called as the bond number. Okay. In certain literature it is also called as Eötvös number. And the inertia to surface tension is called as the Weber number. Now, all these forces can be scaled. Okay. As you know, the viscous forces can be scaled as mu v by L. You will recall your Newton's law of viscosity, and the velocity gradient multiplied by the viscosity is proportional to the shear stress, and that leads to the viscous forces which are directly related to the shear stress, and of course, surface tension is sigma by the characteristic length. So, when you divide these two, you get a non-dimensional number which is mu v by sigma. In a similar manner, the buoyancy is g into delta rho, and naturally the length scale of this bubble or this gas phase, for example. So, the multiplication of these three, g, delta rho and L, will give you the buoyant force, and you can again divide it by sigma by Lc. So, you will get g delta rho Lc square by sigma, which is the bond number. So, if for example, for very small systems, let us say the way we are talking about the injector, the fuel injector, the nozzle of the fuel injector is extremely small. So, this characteristic length is very small, and because of which in the denominator here, since the surface tension has the length scale in the denominator, naturally the sigma by r will be a very large quantity as compared to g delta rho, for example. Therefore, you can also see that the buoyancy forces are not dominant typically in a spray situation, and you can have, let us say, the surface tension dominant flow. It is primarily a surface tension dominant flow, which essentially means it is let us say low bond number situations. And then if you want to create more surfaces, you need some extra energy, and this energy can come from the kinetic energy of the system. For example, the rho v square will be proportional to the inertia forces, and therefore, the rho v square divided by sigma by Lc will give you the Weber number. And naturally, for example, if you have a droplet sitting on a surface and you start blowing air on it, at a particular velocity the droplet will start moving. So, essentially the Weber number increases to a value where the inertia forces they are high enough that surface tension forces are now can be overcome and the droplet can start moving. In a similar manner here, for example, when the liquid is dropping, the velocity increases, the surface tension remaining constant more or less, the velocity increases. So, essentially the inertia force is increasing, and you can see that at certain critical Weber number, that means at a certain critical velocity here, you see that waves have started appearing. Okay. So, the flow of morphology has changed because now new area is getting created, new surface is getting created, and the work which is required to be done is provided by the inertia force, which essentially is coming from the gravitational potential. So, we are pulling we are accelerating this liquid down, the velocity is increasing, the rho v square numerator is increasing, and you will see that at certain critical Weber number you see waves started appearing here. So, essentially our systems, our let us say fuel injector systems are very high Weber number systems, where the inertia force is given by the pressure difference essentially. So, the pressure difference is converted into kinetic energy. This kinetic energy gives you inertia force, and this inertia force when it exceeds a particular value, new surfaces can be created, it overcomes the surface tension, and the surface tension is trying to put this liquid volume together, but now you can break it. You can blow it off and you can create new surfaces, you can impart that required energy through the inertia force, and that is the let us say basis of a fuel injector system. So, here is again the same slide which I had seen some time back, and what you do here is again the same thing. You pump up this particular air pressure, so that air pressure increases, and then the velocity is imparted. This velocity essentially breaks down the liquid droplets into small pieces, and as you can see here, effect of Weber number. So, from Weber number 50 to 200, you can see that a jet of liquid which is oozing out of a nozzle can break down into small droplets, and that is exactly what happens here in the small diameter which are in microns typically. Again I have noted the Weber number definition here, and you can see that as the pressure difference between the injection port here which is supplied by the fuel pump and the combustion chamber here, as the pressure difference increases, you will see the liquid jet oozing out and immediately breaking up into smaller droplets, and you can see multiple droplets being formed, and the energy is supplied by the fuel pump, which essentially gives the pressure difference, which leads to increase in the inertia force eventually, and the high velocity jet comes out, breaks up into small pieces, and that is what is the fundamental requirement. Because as you will recall, we need to break down these particles into very small let us say diameters, so that the air which we have supplied comes in good contact with this diesel spray, and then once the combustion starts, we finally lead up to complete combustion, or as the combustion efficiency has to increase. Otherwise if the droplets are big enough, then the combustion reaction will be limited by the availability of oxygen close to this internal volumes of the liquid, so which we do not want. So, therefore, we want to break it up into small pieces, so that a nice reaction can occur and the combustion efficiency will increase. So, here you see the factors which affect droplet size. So, here is an actual nozzle, an actual photograph, and which you can see a liquid jet and breaking up into small droplets, a liquid spray for example, and here is a photograph of a typical nozzle, and you can see here the small holes at the end. So, there are various designs depending on the engine design, the cylinder head, the availability of space there, what is the design of the combustion chamber, and this particular part goes here. So, you can see the fuel let us say nozzle assembly, the fuel nozzle assembly, the fuel comes from this side, and these two holes are there, so that this nozzle can be inserted into the cylinder let us say chamber, and it can be tightened up. There is an O-ring here which prevents the pressure of the cylinder to come out, and there is a seal here by which this can be fitted to the cylinder head with a proper seal, and then of course fuel will enter from here. It will open up this nozzle, this pin will move up and down, and there is a spring assembly inside this, which I had shown you in the earlier lecture. So, this is a typical let us say fuel nozzle assembly which we have already seen. So, what are the factors on which the droplet size depends? Okay. So, the mean droplet size will decrease with increase in the injection pressure. This is understood because the inertia forces increase, the Weber number increases, and therefore, you will have higher and higher injection pressure will lead to smaller and smaller size. Okay. Then of course, it decreases with increase in the air density. Okay. Now, please remember that the density of air in which you are actually creating this spray is not atmospheric pressure. You are already you're already, let us say, you have compressed the air, and this is already at a pressure of, let us say, 30 or 35 bars when the injection starts. So, the density difference between the liquid diesel and the air, that has reduced actually, because the air is thinner at 1 atmosphere, but it becomes pretty let us say dense at 30 atmospheric pressure. We can easily calculate what will be the density of air at, let us say, 30 bars or 40 bars, and in that condition, when the density is high, you have to do the injection. Okay. So, the mean droplet size will definitely depend on the air density and the viscosity ratio also, because the droplet will come in contact with the air, there will be interfacial shear, and the interfacial shear will lead to further breakdown of the mean diameter of the nozzle. Okay. Then the third point is increases with increasing fuel viscosity. You have to understand that if the viscosity of the fuel is not right here, that means it is, let us say, highly viscous, then in spite of the fact that you are creating a pressure, this viscosity will not lead to proper spray formation. So, in all engines, the temperature of the fuel up to the fuel nozzle, up to the inlet of the fuel nozzle, has to be very precisely maintained. That means there has to be some way, either by some steam heating or electrical heating or insulation or some sort of a heater which heats this fuel, especially heavy oils, for example, in large engines. You want this fuel to be heated up and maintain a proper viscosity, because the viscous forces will have to be controlled, and if the viscosity becomes too high, the spray characteristics will not be very interesting, and you will have lesser combustion efficiency. And of course, increases with increasing size of the the droplet nozzle. Actually, there should be a word nozzle here. So, droplet nozzle, okay, of the nozzle. So, naturally the nozzle size, the bond number let us say has to be low enough so that the primary nozzle diameter, which is here, has to be maintained so that you get a proper spray. So, here is a let us say some types of nozzles or some types of let us say designs which are available. You can have single hole, for example, you can have multi hole, you can also have a pintle nozzle, which is a single nozzle like that, or a pinto nozzle, which is here. Now, it depends on the type, the way let us say this pin which is sitting on this spray. So, there can in a single hole there is only one hole. In a multi hole there are several holes which are there, and you can see a photograph also lying on the right hand side. You can see the photograph from the other side here. So, the nozzle is that part of the fuel injector through which the fuel is sprayed, which you have already discussed. So, what are the functions of the nozzle? It has to do proper atomization, that is very important, which we have already discussed. The distribution of fuel in the chamber. Now, depending on the angle at which you have this multi nozzle, for example, this will spray in various directions, okay, and depending on how the combustion chamber is designed, we would like the fuel to be properly distributed in the combustion chamber, so that the combustion efficiency increases, okay. And this the distribution will depend on the injection pressure, it will depend on the air density and also the thermophysical properties of the fuel. It should prevent the fuel impingement of the wall, because if the spray length is so much that it actually impinges the wall of the cylinder, the wall is cold, mind you, because there is some cooling water also going around. So, you will have liquid which is sprayed on the walls, which is detrimental to not only the tribological health of the cylinder, but also the combustion efficiency, because you are spraying actually diesel on the combustion walls, which are much colder than the inside of the cylinder, and therefore you may have chances of incomplete combustion or carbon being deposited on the walls, which will also affect the overall efficiency of the engine. And then naturally the system should be such that the air fuel mixing is enhanced. Please recall our discussion when we said that the turbulence which is inside the engine, inside the combustion chamber, is a very strong parameter, or very important parameter for controlling the combustion efficiency. Higher the level of turbulence, higher the level of air movement, higher the quality of mixing, better are the chances that the complete fuel will burn. And therefore, as you will recall that diesel engine is an excess air engine, there is always excess air available. It is much larger than stoichiometric. even with a very large let us say excess air ratio or a very lean type of burning, even if you supply a very large quantity of air, still you find smoke coming out of diesel engines, and at high power especially, and that is because the amount of fuel which is needed, if the spray characteristics are not good, if the turbulence and mixing is not proper, then within the time available for complete combustion, you may not get the actual burning efficiency to be high enough, and therefore, before the exhaust valve opens, you already have some unburnt fuel or carbon deposits or smoke, and this smoke comes out of the diesel engine. So, the efficiency of the engine at the end, even if your fuel system is good, your fuel is good, your fuel pump is good, your filters are perfect, but at the end this particular small hole which actually sprays the fuel at a particular characteristics inside the engine is the key of a proper combustion and efficiency of a diesel engine. So, you can see here that how if you have deposits, the cone angle may get affected, the mass flow rate in this cone can get affected. You can even bend the cone depending on you can have a wide cone or a narrow cone or a bent cone depending on where the hole is. Okay, the hole itself can be straight, it can be conical, it can be in a nozzle or a diffuser shape, and there are various let us say patented designs of these cones. You can see some photographs here where you see the spray. They are not even radial. Okay, they are at an angle, because when the spray comes out, it can mix very well with the fuel here, and when we will do the air motion, when we will study the air motion, the swirl inside the engine for example, or squish inside the engine, at that time you will see how the air gets mixed with this particular let us say fuel spray, and why this mixing is very important, because the better the mixing is, the more chances of complete combustion. So, these holes are really a gem of a manufacturing technology, and you can see that in modern times lasers are also used for machining these holes, and you can get various designs and patterns of these holes which are not only radially actually symmetric, but they can also have a offset at an angle. They can be drilled at an angle with a laser beam for example, and several researchers also do for example the spray characteristics, the cold characteristics, as well as the combustion characteristics, and as well as computational combustion or computational fluid dynamic studies to get how exactly the combustion takes place, where is the kernel of combustion, how does the mixing takes place, what is the level of turbulence around this spray, what is the Sauter mean diameter or the mean diameter of the particles which come out of this spray, what is the effect of this the diameter of this hole, the inclination of this hole on the spray characteristics for example, and on the combustion efficiency and things like that. So, with this we have seen the main forces which are applicable in a fuel nozzle system. We have also seen that how Weber number affects the flow characteristics. We have seen some photographs of the nozzles and the spray characteristics. Thank you.